Well, good morning, everybody, and welcome again to today's edition of AP Calculus BC Live. Today, we're going to be looking at topic 10.6, which is comparison test for convergence. I want to thank once again the very talented Kate Yetman for creating, producing, and sharing our intro music with the sultry voiceover by Chris Yetman. The other day, I asked you guys to send in some possible theme songs for Calculus BC because it just doesn't seem important enough to have these lessons daily each day unless we have a really cool theme song. And we have received several of those theme songs, and we're going to make sure that we try to work in as many as possible into our intros or exits during these lessons or even during the lessons. And so if you haven't had a chance to send one in yet, but you've got that musical talent, I want to encourage you to do that and send them up to us, and we'll work as many as possible into these live lessons. So if you don't know, my name is Brian Passwater. I'm a high school teacher in Speedway, and every time we do these lessons, Tony and I will introduce ourselves, and it's starting to get a little bit boring, it seems like, because we're saying the same things over and over again. And so I thought I'd share a little bit more about myself this morning briefly. And I was thinking, what can I tell you that you would need to know that maybe you wouldn't know kind of automatically, and instead of the basic, I'm a married with a couple kids. I thought I'd share a couple things that pretty much sum me up. And so what you're going to see here is a picture. I got a tattoo a couple years ago. I'm a pretty big math nerd. This is the tattoo of the zeta function, the Riemann hypothesis, which I became obsessed with when I was an undergraduate in college. And I wanted to solve this important problem. And so I've been working on it or dabbling on it for the last 15 years or so. And a couple of years ago, I decided to get a tattoo to make it official. My wife calls it my friend finder because if we're out in public and somebody recognizes the tattoo and knows what it is, that's how I meet new friends. Something else you should probably know about me is that I'm obsessed with the TV show The Office. I'm going to be really sad once it leaves Netflix this year. I watch it pretty much every single day. I think I'm on my 25th or 26th consecutive viewing of the entire series. I watched it about 25 times straight through. I love going to do some Office trivia whenever I can find it. Um, so before we get into the lesson today, I want to share a little bit of housekeeping items with you and remind you that every one of these lessons, the handouts and the problems that we do are available to you. You can print them off after the lesson or you can print them off before the lesson and you can follow along. I always include additional problems in each lesson that we're not going to get to. That way you can have some more practice with them. And so underneath each video, there's a hyperlink. If you click on that, it's the same link for every video. There'll be a Dropbox that's shared with you from Isaac Newton, and you'll be able to find the materials that we use each day. We also include in there after each lesson the detailed worked out solutions that our friend Ted Gott makes for us. That way you can check your work and then also see if you're stuck on something, sort of a good path that you could take to solve those problems. Last week, I asked you guys to tweet out some positive things. If you're an AP teacher, I said, hey, tweet out what you appreciate and what you love about your students. And if you're an AP student watching, I said, hey, can you please tweet out what makes your calculus teacher great or so special, or any AP teacher for that matter, and include the hashtag AP Teachers Rock or AP Students Rock. And then each lesson, Tony and I are going to share out one or two of these with the whole group. That way we can share some of the positive things that are going out. And so today, our AP Teachers Rock tweet says, a huge shout out to Ms. B, my amazing calc teacher. Not only does she encourage us to think outside the box and apply what we learn to the real world, but she has also been sending us hilarious math memes this past year. Hashtag AP Teachers Rock. All I know, Ms. B and students, I need to get my hands on some of these amazing, hilarious math memes. And so I'm going to lay down a third challenge, right? I put the challenge out for tweets, and you guys have been tweeting out daily, and we appreciate that. I put the challenge out for some intro music to get us started off each morning, and you guys have responded well to that. I need some math memes in my life, and so if you've got some great math memes, tweet them out. And if I see some great ones, I'll make sure that we include them at the end of each presentation to share out with the rest of the world so we can all celebrate those memes. And then our AP Students Rock tweet says, cheers to all the AP students who are continuing their learning beyond the four walls of GRHS by consistently tuning in to the AP Live sessions. Thank you, College Board. Yes, thank you, College Board, for allowing Tony and I the opportunity to be here each morning with you. Tony and I talk quite often about how humbled we are, how honored and how proud we are to be a part of this and to be a part of your learning each day. We are consistently amazed and impressed by how hard students are working right now when we're stuck at home during the days. And so we're very proud and we're very excited to be a part of this. And we're grateful that you're joining us and that you're continuing to prepare for the AP exams that are coming up this spring. A couple of housekeeping items here again before we start a lesson. Upcoming lessons. Today is April 2nd. If you were here on Tuesday, you noticed the slide said April 1st on Tuesday, and I was genuinely caught off guard and surprised by the date. I wasn't really paying attention to what month or what day or anything it has been recently, and so I was like, wow, it's already April 1st. Well, the dates were wrong. I think Tony played a little bit of a trick on me because he made that slide for me. But I didn't really notice it. And then after my lesson, I received a whole bunch of emails and text and tweets and messages telling me that I had the date wrong. And most people thought it was an April Fool's joke, early April Fool's joke. And so I want to kind of play it off as if it was intentional, but really it was just me not even knowing what day of the week it is or what month we were in. But today is in fact April 2nd, and we're going to be looking at comparison tests. And then Tony's going to finish off our week tomorrow looking at geometric series. And next week, we're going to wrap up Unit 10, the last unit that's tested on this year's exam, by looking at a couple more tests, as well as jumping into some Taylor polynomials, approximations, and error bounds. And then following next week, we're going to have 3 entire weeks, 15 consecutive lessons over amazing, incredible, life-changing AP Calculus BC exam prep and review. This is going to be the best review that you're going to get for this AP exam or your money back. Do not miss those lessons. They're going to be a don't miss, can't miss opportunity where Tony and I are going to do everything we can to make sure you are fully prepared for the exams coming up this spring. So at the end of each lesson, we give an AP practice problem for homework. And then the next day, that becomes our warm-up. And so yesterday, Tony laid down this problem for you all as the AP exam practice. So we're going to look at it today. I hope that you had a chance to try it and maybe work it out a little bit. We're kind of putting a lot of things together from the last several lessons into one good conceptual problem. This is kind of the stuff that the AP exam is going to do typically to see if you really understand and can make connections between the different series and tests and ideas that we're learning so far. And so it's a really good practice to test your understanding and test your transferability of information. So this is the warm-up, and I want to go through the answers somewhat briefly. And I also want to share the answers this way today because of one, because of time, and two, to share out with you, this is what the solution guides look like that we put up on Dropbox after the lessons. And so this is the level of depth and detail that TEDGOT gives us with the solution. So it's a really, really nice worked out solution that we can follow along. Part A says if K is 1/2, use the alternating series test to show that that series converges. And then once we do that, determine if that series will converge conditionally or absolutely. Well, Ted plugged in 1/2 here for K. And then when he plugged in 1/2, the series became just -1 to the n times 1 over n to the 3/2. And so using the alternating series test, he had to do 2 things. Number 1, show that the limit of 1 over n to the 3/2 approach 0, which it did. And then 2, we had to show that the terms are decreasing, or that a sub n plus 1 is always less than or equal to a sub n for some value of n on. And that was pretty intuitive. So both of those were true. And since both of those were true, those were our 2 conditions for the alternating series test. And so then by the alternating series test, that series did converge. And then to figure out whether it converged conditionally or absolutely, then we then look at the series of the absolute value of terms. Well, when we do that, we get a p-series that Tony talked about yesterday, where p was 3/2. And according to our p-series test, since that number is greater than 1, the series converges. And since the absolute value of the terms converged, the series did, then that means the series converges absolutely. And then looking at part B, now we have this new function that b of n is now a of square root of n. So we plug that radical n into the problem, we end up getting this series right here, where we get n to the 1/2 times the quantity k plus 1. And the question says, what would make this series converge conditionally? This is where we really get into some conceptual understanding, because this is sort of like a p-series, right? It's an alternating version of a p-series. And so what would make it converge conditionally? Well, that would mean that it converges the alternating component, but it would not converge if it was gone, right? Conditional convergence means it only converged because the series was alternating. And so if we look at what the series would look like if it did not converge, or if it was not alternating, it becomes this p-series right here. Well, what would make a p-series not converge? Well, a p-series will not converge, it'll diverge if the p-value is greater than 0 or less than or equal to 1. So essentially, to check out when the series converges conditionally, we can just set our exponent 1/2 to the times k plus 1 between 0 and 1. And then we can solve that inequality. And Ted kind of worked this all out here really mathematically for us. But another way to think about this is just to solve this inequality by multiplying everything by 2 to get rid of the 1/2. And we get 0 is less than, k plus 1 is less than or equal to 2. And subtracting 1 from all three parts, we get that k is greater than -1 and less than or equal to 1. And the question wanted all integer values of k. And so the only integer values that would work would be 0 and 1, since we cannot include the -1 in our answer. And then finally, looking at part C, we have a third function. C of n is a of n to the -2k. And we want to show now that there's no real value of k, where that C of n is the harmonic series. Well, think about what that harmonic series is from yesterday. The harmonic series is just a p series, remember, where p is equal to 1. So it's just 1 over n. And we want to show there is no k value where that would be harmonic. Well, this is what the series looks like right here. And if it were harmonic, that means the exponent would have to be 1. So when it says show there's no real value, whenever an AP question says show something, really what that means is treat it as if it said find, right? If it says show there's no value, it's kind of asking you to say find what k would be. So you would solve for it, and whatever you get, you have now shown whatever answer they wanted. And so Ted just set this exponent equal to 1, because that's what would make it harmonic. And then we start to solve this quadratic equation. It becomes 2k squared plus 2k plus 1 is equal to 0. It doesn't factor, but we can use a quadratic formula. And when we do the quadratic formula, look what happens. Inside of the radical, we get this -4. And we know that the square root of a negative number is going to be an imaginary number or a complex number. And so in this case, the only way we can solve for k is to get an imaginary answer, which is not a real number. So we've now shown that there's no real numbers of k that would make that work. So thank you, Ted, for creating such great, detailed, worked out solutions. You're going to see solutions like this, as well as solutions to all the problems there in the Dropbox following our lessons. So today, let's talk about what we're going to be learning about. And I mentioned it already. We're going to be using the direct comparison test to learn about convergence and divergence, as well as the limit comparison test for convergence and divergence. And then throughout the lesson, we're going to be hopefully tying all these previous tests together so you can see how they all fit in and intertwine in different types of problems, right? And so remember the tests that we've talked about so far, so we're going to limit ourselves to just the tests that we've done here. We know there's more tests that some of you have seen if your class has gone further in the curriculum already, but we're going to limit ourselves to just certain tests to see if we can use these tests. And we've talked about the nth term test for divergence. We've talked about the p-series, right, test. We'll be talking about the direct comparison test today, as well as the limit comparison. We did the alternating series test the other day, as well as the idea of absolute versus conditional convergence. And so we're going to do all of our problems with that. We're not going to be using the geometric series, which we'll do on Friday this week with Tony, and we're not going to do anything with the ratio test because that will be next week, right? What should you know already that to make yourself successful? Well, hopefully, if you've been following along, you've gotten lots of practice at evaluating limits at infinity. We remember our P-series rules for convergence from yesterday, and then our end term test for divergence from last week. And by the end of the lesson, we'll not just know how to do basic mechanical problems of direct and limit comparison, but we'll have a depth of understanding that will allow us to tackle more of these abstract problems that are making a lot of connections, like if 0 is less than A is less than or equal to B for all n, and the series of A sub n diverges, then what do we know about the limit terms of B sub n? So in order to answer a question like this, we're going to have to understand a couple of things. Number one, how does the direct comparison test work and what does it tell us? And then second of all, how can I apply that and use the nth term test or the idea of convergence in general to make a decision about B sub n if we can at all. So the guided practice is what we would call like the notes part of our lesson. And so here's the notes for today. And before we actually dive into what the direct comparison test is, let's play a little game of logic, shall we? It'll be a pretty easy game, I promise. And I want us to think about two different situations. So situation number one, when my children were younger, this is a true story, by the way, adapted a little bit, but this basically happened to us. When my children were younger, we went to a local carnival and we rode down those big slides, right? You know, I'm talking about those really big slides where it's like you get on those burlap sacks and you ride down the big yellow slides. Has a little bump in the middle. So we all rode down those big slides as a family. We had a little bit of a race. And once we were done, my son wanted to go on it again, but he wanted to go alone this time. He was pretty young at the time, maybe 4 or 5 years old. He wanted to go again, but he wanted to go alone. Well, unfortunately, when he went back to the line, guess what? He was not tall enough, right? Remember these little signs that you have to be this tall to ride these rides alone. So here's my son. He looks kind of like this, right? He was pretty sad because he wasn't quite tall enough. And if you watched us yesterday, you got to see Tony bring out his guitar and kind of show his talent on the guitar. And I felt a little bit left out that Tony got to share his talents. And so I thought today would be a good day to share my talent of drawing, because this is pretty much a spot-on picture of my son. If you see him, you recognize him right away. He's the little blue guy that's skinny that has a little frowny face on him. So he was not quite tall enough to ride the ride alone. Well, my daughter's a couple years older than he is, so she's taller than he was at the time, and she wanted to ride the ride alone. Well, if she's taller than him, do you think that she is tall enough to ride? Take a quick second and think about that. My son wasn't tall enough. I drew a little picture of him. My daughter is taller than he is. Is she going to be tall enough to ride? Well, hopefully you're realizing we really don't know yet, do we? Right? Because he wasn't tall enough, and she's taller than him. So maybe she is this tall, where she's taller than he is, but she's still not quite tall enough to ride. Or maybe she's a lot taller than he is, and she did barely reach the height that we need. We don't really know. We don't have enough information to compare the heights to determine whether she was tall enough to ride or not. Well, later on that same day, situation number two, we decided to play some carnival games. And both of my kids played way too many games, like we always did. And they came away with a whole bunch of tickets to redeem for some prizes at the end. And my son's always the lucky one. So he won a jackpot on one of those games. So he had a whole bunch of tickets, right? So he ended up getting more tickets than my daughter did. And there was this really big prize that he wanted. I can't remember what it is now, but you know how they always have those big prizes on the shelf where it's like 10 million tickets to win. And no one ever has any chance of winning it because you look down in your pile, you have like 48 tickets. You're like, oh man, 9 million away. I could have had that. So my son wanted this prize, but he was like 5, so he doesn't understand the idea of how numbers work that well. But he didn't have enough money to win the tickets. Well, my daughter also wanted the same prize, right? So she wanted the same prize, but she had less tickets than he did. So do you think that she had enough tickets to get the prize? Well, obviously, if less than he did, then certainly no, she wouldn't, right? Now, the logical thing would have been, hey, why don't you guys pool up your tickets, put them together, and have double the tickets, and then go in together and get something bigger? But due to the sibling rivalry they always had, that never would have worked, right? So they all wanted to buy their own stuff, and neither one of them had enough tickets to buy whatever that big prize was individually. So both of those situations are going to set us up for what we're going to be doing today, which is the direct comparison test. And they're going to show you how it works and also some things where it doesn't quite work the way you want to, right? And so Going back to our lesson from yesterday about P series, look about the series 1 over n squared, right? And we know from yesterday that that's a P series. And because the P value is 2 and 2 is greater than 1, that series converges, right? P series says if the P value is greater than 1, then the series will diverge or converge, I apologize. But what about these two series? What about the series 1 over n squared plus 1? Or what about the series 1 over n squared minus 1? Well, those aren't technically P series, right? A P series is just 1 over n to the P. It doesn't account or doesn't allow for us to have anything else being added or subtracted to it. It's just 1 over n to the P power. It doesn't allow us to have this plus 1 or this minus 1. And so we can't apply the P series directly to this. Now, hopefully, our intuition, our gut instincts will tell us or give us a hint about what this is doing, right? I mean, what do you think? If 1 over n squared converges, what do you think is going to be happening with, intuitively at least, 1 over n squared plus 1 or 1 over n squared minus 1? Well, hopefully we understand that that little plus 1 or that little minus 1 in this case isn't going to really do enough to impact whether or not this series converges or diverges, right? So if 1 over n squares converges, it would make sense that 1 over n squared plus 1 would also converge, or 1 over n squared minus 1 would also converge, because that shouldn't change the outcome of the problem. Now, certainly, if it converges, it'll be a different answer. It'll converge to a different number, but it's still hopefully going to converge. Well, how do we take that intuition or that kind of that gut feeling and apply it more mathematically? And that's where the direct comparison test is going to come in. And then later on today, the limit comparison test will come in as well. So here's what the direct comparison test says. If A is greater than 0 and B sub n is greater than or equal to A sub n for all values, then if B sub n, if the series of B sub n converges, then so does the series for A sub n. And if the series A sub n diverges, then so does the series for B sub n. It seems like a pretty simple idea on the surface, and it really is, except sometimes we get these little nuanced problems where we have to be careful what we know and what we can apply, because just like with the nth term test, students will often misapply or misuse or misunderstand what this test actually says, right? These are if-then statements. If you remember much from your class, this is a conditional statement. And when we have a conditional statement, we don't get to assume that the converse or the inverse are true statements as well. And so sometimes students will use the converse or assume the converse is true or assume that the inverse is true when usually it's not. And I'll explain what I mean by that here through a couple of examples. So I'm going to take a step back for a second, and we're going to look at the direct comparison test again, and we're going to see what it says, but also we're going to see what it does not say, right? And so I'm going to preface this. I'm going to put down here on the bottom of the page for a second to all of the teachers that are out there, please do not send me, please do not send me any hate mail over this, please. And here's what I mean by that is I'm going to step back and I'm going to be a little bit unmathematical for a second, okay? A lot of times with series in particular, as math teachers, always trying to be very precise, very technical, and very correct. But when we do that, it involves a lot of symbols, a lot of notation, a lot of vocabulary, a lot of mathematical jargon. And when we do all those things, sometimes we take some basic, simple ideas and we complicate them unnecessarily and it ends up confusing people. So what I want to do is take a step back from all this technical mathematical precision for a minute and just get to the heart of what this really says. And so we're going to look at this from a more kind of non-mathematical, logical way to make sure we really understand what this test is saying and what it's not saying. And then we're going to come back to the mathematical side and prove all these things or do all these things properly, right? So when I'm naming some things, yes, I know this is not mathematical, but I think it's going to give you a better idea of what's happening. So please don't send me any hate mail until after you see the whole lesson. And then in which case, if you still don't like it, feel free to do that. So here's how I think about the direct comparison test. I always imagine all series as either living in this land of divergence, right? Up here is sort of this land of divergence. So up here is where all the series diverge would live. And then down here is the land of convergence. So all the series that converge live down here. And then there's this magical sort of dotted line separator that divides all of the divergent series from all of the convergent series. And every time we learn a test, when we learn the nth term test, when we learned the p-series test, when we learn the alternating series test, today when we learn direct comparison or limit comparison or the ratio test next week or geometric series tomorrow, every time we learn a different test, really what we're doing is we're trying to figure out where that dotted line is. We're trying to figure out where's that separation between what makes a series diverge and what makes a series converge. And depending on what type of series we have, depending on how that series looks, how we find that dotted line, how we find that separation, a little bit. So we learned when we had P series, that dotted line was based off of the value of P, right? And so if the P value was not more than 1, the series would diverge. So up here in this world of divergent series would be things like the harmonic series of 1 over n. But down here in the land of convergence, we would have series like 1 over n squared, right? We might have some series up here in the land of divergence, just something like -1 to the n power. That would diverge by the nth term test because the terms don't approach 0, right? Or we might have down here in the land of convergence, maybe the alternating harmonic series, -1 to the n over n. So we have these a whole bunch of divergent series up here, a whole bunch of convergent series down here. So let's think about these statements that the direct comparison test is making. Let's also think about what it's not saying, which would be really important here in a few minutes. So we're going to call this series of A sub n capital A to make it easier. And we're going to call this series of B sub n capital B to make my work a little bit easier. And remember, this is a key part here, right? That A sub n is less than or equal to B sub n, which means that the series A is less than or equal to the series B. And so if the series B converges, that means that capital B is somewhere down here, right? It's somewhere down here in this world, this land of convergence. It's a convergent series. So what can that tell me about the series of A? Well, since A is less than or equal to B, then A has to be either below or equal to B, which means I can only go down in this direction. Well, if I go down from wherever series B is to a lower value, then certainly series A is still going to be down here on this land of convergence, right? So if B converges, so does A, no problem. Well, what about the second part? What if A diverges, right? So now we know that capital A is going to be somewhere up here in this situation, in this land of divergence. What do we know about series B? Well, B is bigger than A. So if B is bigger than A, we have to go up, right? We're going higher, it's a higher value. Well, if A diverges and B is always bigger than A, then B has to be up here somewhere. Well, if I'm going up and I'm already in this land of divergence, certainly B is also going to have to be in that land of divergence. So those two ideas are pretty straightforward, but here's where I think it gets a little bit tricky. And here's where that first situation I talked about with my son and my daughter writing that slide comes into play. Because what if series A converges, right? What if we know series A is down here somewhere? So what if series A converges? Remember, we know that series B is above series A. But if A is down here in this convergent area and I'm going up because B is higher, how can we figure out whether B is still going to be in that area of convergence? It could be, right? I could go up and still be in the land of convergence. Or how do we know whether or not we go up so far that it passes over this line into the land of divergence? We really can't tell, can we? And then conversely, what if series B diverged, right? What if series B diverged and we know that A is less than B, so A is going to be lower? Well, again, how do we know how far lower it is? How do we know if it's low enough, but it's still going to be in this divergent area, or whether somehow it was low enough that it crossed over into this land of convergence? Again, we don't know. And so when we're doing the direct comparison test, we have to be really careful about what series we're using to compare with and what really we can say about it, right? And so I like to kind of draw these pictures, especially with more of the abstract conceptual problems where you don't actually have a real series to work with, because it helps me understand what I can and cannot say about the different series. So let's see this in action, right? So we started off this idea with this series right here of 1 over n squared plus 1. And we're going to use the direct comparison test to sort of hopefully reinforce or solidify what we thought intuitively that this should converge, right? And so our natural idea is we've got to compare it. Whenever you do a comparison test, you have to compare it to a test or a series that you know what it does, right? And so the most natural comparison is going to be 1 over n squared. Because I know that 1 over n squared converges. How do I know it converges? Because it's a p series where p equals 2. And yesterday we learned that a p-series where the p-value is more than 1 will converge. And then this series right here, remember it says, look, if the series that you're comparing it to, if this series is less than this series, then that means it's going to follow the same convergence rules, right? And so essentially, here's what we have. If I kind of draw this dotted line again, I know that this series, 1 over n squared, is down here somewhere in this convergent world. And then now I can compare the terms. Well, look at the terms 1 over n squared plus 1 compared to 1 over n squared. Well, since I'm adding 1 to this denominator, that means that this denominator is always going to be a little bit bigger than this denominator, right? It's always going to be 1 more than this one. Well, if this denominator is bigger than this denominator, that means that this fraction is going to be less than that fraction. And so since these terms are always less than these terms, that means that this series is going to be less than this series, right? Well, if it's less than this series, then I know that it's going to be going downward somewhere, and it's still going to be in this area of convergence, right? So by the direct comparison test, since 1 over n squared plus 1 is always less than 1 over n squared whenever n is at least 1, then the direct comparison test tells us that because of this, 1 over n squared plus 1 from 1 to infinity converges. And we're going to say by the direct comparison test. And whenever we're doing a comparison test, it's really helpful to tell what we compared it to. We compared it to 1 over n squared. So that's a really nice example of how the direct comparison test would work for convergence. What about how might it work for divergence? Well, example 2 is 1 over the square root of n minus 3, and the natural test to compare it to would be the series, hopefully, 1 over radical n. 1 over radical n, don't forget, is the same thing as 1 over n to the 1/2 power. And this is also a p-series, right, where p is equal to 1/2. Well, because p is equal to 1/2, that's less than 1. So that means that this series diverges, right? It's a divergent series. And so that means if I were to draw my little picture here, that the 1 over radical n series is going to be up here somewhere, right? Well, hopefully, the only way I'm going to be able to make any kind of determination about this series is if I can somehow show that these terms are bigger than these terms, right? Because if this is up here, if these terms are all bigger than 1 over radical n, then I know that it's going to be higher, which means it would still diverge. Well, let's see if we can show that. 1 over radical n minus 3, if we compare that to 1 over radical n, notice we're starting here at n equals 10. Well, we started at n equals 10 because if we started at anywhere below 10, like 9, for example, the square root of 9 minus 3 would have given us 0 in the denominator, which would have been an undefined value. And so we were just going to be safe and start at 10. Well, this fraction right here, since we're subtracting 3 from these denominators, that means this denominator is always going to be a little bit less than this one. And if this denominator is less than this denominator, that means that this fraction is going to have to be greater than that fraction, which means my series, since these terms are all greater as long as n is at least 10, it means that this series is going to be bigger than this series, which means it's going to be up here still. which means we're going to be divergent, right? And so that means that this series diverges, and then we're going to say by the direct comparison test, and then to the series 1 over square root of n, like that. So those are a couple of examples of how we can use the direct comparison test. We're not going to look at example 3, but it's there in case you want to try it. And I would encourage you, if you try this, to see if you can solve it without using any geometric series, right? Because we haven't done geometric series yet. So I purposely threw something in there that has some geometric series in it to see if we can solve it using some partial sums ideas from the other day. Now, example 4 is a little bit more of an abstract question. That's where we're going to really get to the heart of if you understand what these things mean and how we can apply it, especially if we don't have a given explicit function or a given series to work with. And so the same rules apply. If 0 is less than a is less than b, and if the series a sub n diverges, which of the following must be true? That's the key here, must be true. And so here's what we know. We know that the series of a sub n is somewhere up here, right, in this divergent world. So if a is up here, what do we know? Well, this is a really neat question because take a second and look at your A, B, C, and D. I'm going to give you a few seconds. I'm not going to put a timer on here, but I want to give you a few seconds and see if you can think about which ones you think must be true. And to make it a little bit more interesting, I'm going to tell you it's possible that none of them must be true, or one of them might have to be true, or more than one. So I'm not going to say whether there's one answer or more than one answer or no answers, but take a few seconds, take a look at these and see if you can figure out how many or which ones, if any, must be true. So I'm going to start with the one that might be the most obvious compared to what we've just been talking about. Since we know that B is greater than A, then to get to B, I have to go up, right? So the series for B sub n is going to have to be greater than A. It's going to be up here somewhere. So what do I know? Well, if A diverges, then B has to also diverge, right? So we know for certain that D must be true. But what about the other ones, right? We know that the series for A diverges. What about this, C? This is just the alternating version. And we did learn that it's possible that a series might diverge, but yet if it alternated, it would converge, right? That was the idea behind Tony's lesson yesterday, talking about conditional convergence, right? Well, it is certainly possible that this alternating version could converge. Unfortunately, we don't know if it has to, correct? So this doesn't have to converge. It could, but it's not true. I mean, in terms of it has to be true. So we can cross C off. And then what about A and B? These are kind of the same ideas. The limit of A sub n does not equal 0, and the limit of B sub n does not equal 0. Well, we know that A and B both diverge, but does that mean that their limits don't equal 0 of the terms? And the answer to that is no, right? Because the in-term test from the other day says if the limit as n approaches infinity of a sequence does not approach 0, if the terms don't approach 0, then, right, arrow, I'm going to put then there, the series diverges. That's what the in-term test says. We don't get to make any other assumptions about that, meaning here we know that the series diverges. We don't get to go backwards and assume that this is true, right? That would be called the converse of this conditional statement. And just because you have an if-then statement doesn't mean you can turn it around and still assume that it's true, right? A really simple example of this would be, I live in Indianapolis, right? So if someone lives in Indianapolis, then they live in Indiana. That's a true conditional statement. If you live in Indianapolis, then you live in Indiana. Well, if I turn that around with the converse, it would say, if someone lives in Indiana, then they must live in Indianapolis, which is clearly not a true statement, right? And so we don't get to turn statements around. If something diverges, it's very possible the limit of its terms could approach 0, right? For example, what if A sub n was just 1 over n? What if that series was just the harmonic series? That certainly diverges, doesn't it? The terms still approach zero. So A is out and B is out in terms of they don't have to be true. It's possible they might not equal zero, but they're not guaranteed. So the only correct answer was D. You're going to see a lot more of these abstract conceptual problems on the file in that Dropbox folder. So it's really good practice to jump in and try some of these because it really will test the nuances of how well you actually know these different tests and these different theorems. So I want to show you a quick example of why we need the limit comparison test, because the other series that I gave you was this 1 over n squared minus 1 series. But in this case, it would be more natural. What series would we compare it to? Well, my first instinct would be to compare it to 1 over n squared, right? That would be the natural choice. Well, think about where 1 over n squared is. Well, that is certainly going to converge, right? Because this is a p series where p is 2. But then if I'm comparing it to this series right here, 1 over n squared minus 1 is actually going to be less than 1 over n squared whenever n is greater than or equal to 2. Because if I'm subtracting 1 from this denominator, it's going to make this fraction bigger than this one. Oops, I had that backwards, didn't I? I caught myself this time. 1 over n squared minus 1 is bigger than 1 over n squared because if the denominator is a little bit smaller, it's going to make the overall fraction a little bit bigger, isn't it? So if 1 over n squared is down here and 1 over n squared minus 1 is bigger than that, that means that that series is going to be a little bit bigger. But that gets into that problem we had of like my son and my daughter and their heights, right? So if I'm going a little bit higher, how do I know how much bigger it is? Is it big enough to cross over that sort of imaginary line to this world of divergence? Or is it not enough to cross over? Well, our intuition might tell us, well, clearly it's going to still converge, but we can't use the direct comparison test with 1 over n squared to do that because it's not going to give us the right comparison that we need. Now, there are some ways that we could do this. We could come up with a test, right? We can compare it to something like 1 over n to the 3 halves. We could do some stuff like that. But it starts to get a little bit trickier to guarantee that the terms are always less than something else. And so it leads us into this other test, a little bit more powerful test, a little bit more robust, called the limit comparison test. And all the limit comparison test says is if A is positive and B is positive, then if you took the limit of the ratio from A over B, if that equals L, where L is a finite, meaning a real number and positive, then both of those series will either both converge or both diverge. And so what we're doing is we're trying to find a comparable series like we were doing with the direct comparison test. And then all we have to do is take the limit of their ratios. And if that limit equals a positive real number, right? Got to be positive, it's got to be a real number, then we know that those two series behave the same. Meaning if one of them converges, the other one does. If one of them diverges, the other one does. They're going to live sort of in the same world. And so let's see how we can apply that to that 1 over n squared minus 1 problem. It's going to make the most sense, again, to compare this to 1 over n squared. Well, what do we know about 1 over n squared? Well, certainly this series will converge, right? Because the p-value is 2. But using the limit comparison test, we're taking the as n goes to infinity of 1 over n squared minus 1 divided by 1 over n squared. We're going to divide the ratio of those two sequences. Now we're going to do a little bit of manipulation here with our fractions. We're dividing by a fraction, so really we're taking 1 over n squared minus 1 times n squared over 1. And then that becomes, if I go ahead and multiply that, we're going to get n squared on top over n squared minus 1 on bottom. Well, the limit as n goes to infinity of n squared over n squared minus 1 is just going to be 1, right? It's the ratio of those coefficients. And the limit comparison test says if that limit equals a positive real value, hey, 1 is a positive real value, then the series that we want to know and the series that we are comparing it to will have the same outcome. And so since 1 over n squared converges, then 1 over n squared minus 1 is also going to converge. And so we can say that this series converges by the limit comparison test to 1 over n squared. So that's a really good example of why we could use the limit comparison test. The limit comparison test, really what it does is it confirms all those intuitions that we might think should work. So the really key about limit comparison test is to know which series to compare it to. And the easiest way to do that is ignoring everything except for the largest exponent in the numerator and the largest exponent in the denominator. If you look at just those and reduce that ratio, that's the series that you should compare it to. So for example, in this case, I would compare this series to n squared, that's the largest power on top, over n cubed. And then if we reduce that, we can compare this to simply 1 over n. So if I was going to do the limit comparison test, I would do the limit of 1 over n compared to this series right here. And we know when we do the limit comparison test, if you choose the right series to compare it to, they're going to have the same outcomes. And so since 1 over n is a harmonic series, a p series where p is 1, since this diverges, I know that the original series is also going to end up diverging. And we can set up that ratio and solve that as well. Something like this one, right? It has some radicals in it, but it's not going to be too tricky. The square root of n plus 1, well, the largest thing on the top is just going to be that radical n. And the largest power, the most dominant power on the bottom is this n to the fourth. So if I try to reduce this series, n to the 1/2 on top and n to the fourth on the bottom is going to end up being n to the 7/2 if I subtract those powers. Well, it's another p series where p is greater than 1 in this case. So I know that both of these series are going to end up converging once I do my limit comparison test. I'll leave this last one for you to try at home as we get ready to wrap up here today. It's a nice little problem. I always like to give some regular problems where you're kind of manipulating, right? This kind of goes from easy to medium to more challenging questions. A basic question, a little bit more interesting one with some radicals involved, and then something that's a little bit more non-specific, right? Where I have a K involved, we had to sort of have some ambiguity there. If you can do problems like that, then you know you really, really understand what these concepts are. So I'm going to leave that one for you so you can try that. And so there's a couple different problems here that we can try. And again, there's a whole bunch of them in there that you're welcome to try. And Ted has all these worked out solutions for you, which is really going to be some good practice. And then I want to point out something that's in the check for understanding. There's an activity that we'll put in the Dropbox that's called which does not belong. And really, each question has 4 different series, and then there's different answers that could be correct, right? So there's no like this is the right answer, but it's just getting you into the habit of recognizing series, right? When we did integration, think back to integration. With integration, the most challenging part to integrate was recognizing what strategy to use, recognizing what type of integral to use. Is it going to be an inverse tangent type problem? Is it going to be a U substitution problem? Is it going to be a problem that's going to end up being a natural log when I'm done? Am I going to have to use integration by parts? Am I going to have to use partial fractions, right? The hardest part of integration is identifying what type of question it was. And then once you knew what it was, then you sort of have some procedures to go about and to do it. Well, series are very similar to that, where the most challenging part is recognizing on the front what kind of problem it is and what strategy we should use. And so this is a really good activity to get you into that habit, just practicing that skill of recognizing different types of series so we can get a better sense of how to categorize them and how to start these problems. And so there'll be 4 problems and you're going to identify which one is different from the rest. And there's different reasons. Sometimes it's because one of them diverges and the rest of them don't. Or sometimes it's because one of them is, or all of them are geometric except for one, or all of them are p-series except for one, or all of them fail the nth term test except for one. So there could be some multiple different answers, but you can play around with it and we'll have that file in the Dropbox for you as well as a couple of other of these check for understandings. And then I want to point out, don't overlook this last practice 3 problem because it really gets to the heart of your depth of understanding of, here's an intro, right? If something is true, and so question A, if the series of B diverges, there's 4 things here. This is not a multiple choice question, right? Notice I didn't put A, B, C, or D for the choices. For each one of these, you're going to decide if these conclusions are always, sometimes, or never true. They're a little bit trickier than you think, and they're really going to make you think about these ideas because we don't have an actual given explicit series to work with. You're going to have to think about how all these things connect. So try those out, compare your answers with the answer keys that you see. So let's talk about what we did today. We talked about the direct comparison test and we talked about the limit comparison test. Hopefully they start to make a little bit more sense to you today. A couple of things that we see students do incorrectly on this is sometimes they will misapply it. And when I say misapply it, that's what I was talking about with that first situation where you compared it to a series, but however, the connection between the two series doesn't allow us to make a valid conclusion, right? So we got to be careful that we're picking the correct series and that we're making the correct conclusion if we can even make a conclusion. And then with the limit comparison test, it's important that the value L that we get, this is not the actual sum of the series. Sometimes students think because it becomes a number, you do the limit comparison, you get 2 or you get 4 or 1 or something, you think, oh, that must be the actual answer to the series. Remember, we don't actually know what the answer to these series are. All we're deciding is, do they converge or do they diverge? We don't actually say, what do they converge to until tomorrow when Tony introduces us to the geometric series test. And then also don't forget the value L needs to be a positive value. If it equals 0, then that test failed, and most likely we compared it to the wrong series. If you don't get a positive real number, then you probably compared it to the wrong series. You made a mistake on how you should simplify or reduce that. So your AP practice for the day, I'm going to leave you with this. Another nice conceptual problem in the beginning. I'm going to give you 3 different sequences, A sub n, B sub n, and C sub n. Notice K is greater than 1. This is a 4-parter. Wow. I'm really setting Tony up for some challenges tomorrow. I'm learning as I write these AP exam practice problems that when I give a lesson, I can make the problems really, really hard because then Tony has to deal with the aftermath. He has to walk you through them. If you saw yesterday's AP practice problem or yesterday's warm-up, I mean, that Tony did, he did a masterful job explaining it because I really laid the gauntlet down and thought I would really trip him up, but he came through. Then I also realized when I have his AP practice problems on his lessons, then I'm going to be doing those during my warm-up. And so I'm going to start making his practice problems that he gives you a little bit easier. That way it makes my life easier, and I'll make the challenging ones for him to deal with. But we have 4 parts there, and this is, again, in that file in the Dropbox. But if you don't have access to a printer, or you don't have a chance to get to that Dropbox, take a quick picture of this and see if you can't try some of these. And I'm going to encourage you to really try these because these 4 problems connect all these ideas that we've been talking about, all these series tests and all these connections. You're going to have a chance to work with them all together in one problem and really give you a good feel for whether you're ready or not for the AP style questions that you might see. Wonderful. So as always, we want to remind you that the College Board's well aware that sometimes there are some issues with getting connected or getting mobile tools or connectivity to either access AP Classroom or the AP exams that are coming up. If you or anybody else that you know might have a concern or an issue with that connectivity, please reach the College Board directly at the website cb.org/tech, and they'll make sure they work with you to get you what you need to be fully prepared and ready to take the AP exams. And I'll leave you with this quote. You miss 100% of the shots you don't take, Wayne Gretzky by Michael Scott. If you're a fan of The Office, you will understand that reference. And even though it's a little bit silly, it is true. If you don't take the shot, there's no way that you can make it. And so thank you all for being here, for taking your shot, preparing for the AP exam, and to give yourself the best chance to be fully prepared for what's going to be happening this spring. Thank you for joining us. Thank you for watching. Don't forget to join in tomorrow for Tony's lesson over geometric series. Is going to be a great one. Have a great day, you guys.